Probability is the mathematical measurement of uncertainty. It quantifies how likely an event is to occur, ranging from 0, which is impossible, to 1, which is certain. We define probability as a ratio. Specifically, the number of favorable outcomes divided by the total number of possible outcomes. This ratio provides a precise language for managing risk and making decisions in an uncertain world. The frequentist view defines probability as the long-run frequency of an event. If we observe a process, like flipping a coin, repeatedly, the ratio of heads to the total number of attempts will stabilize. As we increase the number of experiments, the relative frequency of the outcome converges to its theoretical probability, which is 0.5 for a fair coin. This perspective depends entirely on the concept of a repeatable experiment. It treats probability not as a state of belief, but as an objective limit of experimental reality. The Bayesian view shifts our perspective on probability. Instead of seeing it as a static frequency, we treat it as a degree of belief. We start with a prior distribution, representing our current knowledge. This is our baseline hypothesis. As new data arrives, we integrate this evidence into our model. These points represent incoming information that challenges or refines our initial assumption. The Bayesian process mathematically updates our belief, transforming the prior into an updated posterior. This is a dynamic, continuous learning process. Discrete variables take on specific, countable values like the faces of a die. In contrast, continuous variables exist on a spectrum, like measuring weight or time, where any value within a range is possible. Expectation is the weighted average of all possible outcomes. Imagine a game where you have outcomes with different probabilities. The expectation represents the long-term average. Variance measures the spread of these outcomes. It tells us how far, on average, results deviate from the mean. A low variance means results are clustered closely, while high variance implies a wide distribution. Independence means that the outcome of one event provides no information about the other. For example, flipping two coins simultaneously. Correlation measures how two variables move together. However, just because two things correlate doesn't mean one causes the other. Correlation is often just a coincidence or shared influence. The law of large numbers states that as the number of experiments increases, the experimental average gets closer to the theoretical expected value. Early results show high volatility, often mistaken for luck. However, as more trials are performed, the fluctuations dampen and the sample mean settles near the true probability. This mathematical certainty is the reason why casinos remain profitable and why long-term statistical trends are predictable despite individual randomness. The central limit theorem is a cornerstone of statistics. It states that when we sum many independent random variables, their distribution tends toward a normal curve, even if the source data is not normally distributed. Imagine we take samples from any distribution, even one that is skewed or flat. Initially, the data looks irregular. As we increase the number of independent samples we add together, the distribution of their sum begins to take a specific shape. Regardless of the original shape, the sum converges to the familiar bell curve. This mathematical phenomenon allows us to make powerful predictions about population averages. This theorem is why the normal distribution appears everywhere in nature and science, forming the bedrock of modern statistical inference. Pearl's ladder of causation helps us understand how we reason about the world. It consists of three distinct levels of cognitive ability. The first rung is association. This is seeing patterns in data. If we see ice cream sales and sunburns both rising, we associate them, even if one doesn't cause the other. The second rung is intervention. This moves from passive observation to active control. We ask, what happens if I do this? It's about changing a variable to see the result. The top rung is counterfactuals. This is the ability to imagine what would have happened if we had made a different choice. It is the core of human regret and scientific discovery. Moving up this ladder allows us to progress from simple data mining to true understanding of cause and effect. Bayes' theorem provides a logical framework for updating our beliefs as new evidence arrives. It bridges the gap between prior knowledge and actual observation. The formula is elegant. PAB is the posterior, our updated belief. It equals the likelihood of the evidence given our hypothesis times our prior, divided by the marginal likelihood of the evidence. The posterior represents our new level of confidence. The likelihood captures how well our hypothesis explains the incoming data. Imagine the overlap as the shared probability space. Bayes' theorem refines this intersection, constantly tightening our understanding of the world. A test that is 99% accurate seems reliable, but when applied to a rare disease, the results can be counterintuitive. This is the diagnostic paradox. Imagine 100 people. Only one person has the disease. The test is 99% accurate, meaning it correctly identifies the sick person and misses 1% of healthy people. When we run the test, the sick person correctly tests positive. However, because the test has a 1% error rate on healthy people, one person out of the 99 healthy ones will also test positive. Now, if you test positive, you have one true positive and one false positive. You only have a 50% chance of actually being sick, despite the 99% accurate test. This highlights why prior probability is essential. In rare conditions, the volume of healthy people producing false positives can overwhelm the few true cases. In traditional systems, an answer was a single rigid point. It told you what to believe, but it never told you how much to trust it. Modern AI systems use uncertainty quantification to provide a confidence interval. Instead of a single number, we look at the range of possibilities. A narrower distribution means high confidence, while a wider curve signals that the system is less certain about its prediction. Quantifying uncertainty is the key to building AI we can actually rely on. It reminds us that behind every prediction, there is a probability, not just a fact. Calibration is the ultimate test of a probabilistic model. It asks a simple question. When you predict a specific likelihood, does reality reflect that prediction? If a model forecasts a 70% chance of rain for 10 days, a well-calibrated model should show rain exactly 7 times. If it only rains twice, the model is poorly calibrated. It was overconfident in its prediction. The true value of a probabilistic model is determined by this calibration. It is the gold standard for integrity in predictions. Some probability problems involve variables so complex that traditional pen and paper calculus becomes impossible to solve. By running thousands of random trials, we can approximate the answer. The ratio of successful outcomes reveals the result. As we increase the number of simulations, our estimate converges toward the true value. This is the power of the Monte Carlo method. The birthday paradox is one of the most famous examples of how human intuition fails when it comes to probability. If you had to guess, how many people would you need in a room to have a 50% chance that at least 2 share a birthday? Most people intuitively guess hundreds, but the answer is surprisingly low, just 23 people. The reason is that we aren't looking for a specific birthday. We are looking for any pair. With 23 people, there are 253 possible pairs that could potentially share a birthday. With 23 people, the probability of a shared birthday is over 50%. Our brain fails here because it fixates on one person, rather than the exponential number of relationships within the group. That is the birthday paradox. You are on a game show. There is a car behind one of these 3 doors, and goats behind the other 2. You choose door 1. Now, the host, Monty Hall, who knows what is behind the doors, opens door 3 to reveal a goat. Most people feel it's a 50-50 chance, but that is incorrect. Your initial pick had a 1 in 3 chance of being right. The car must be behind door 2 or 3. Because Monty opened door 3, the full 2/3 probability of those doors shifts entirely to door 2. By switching, you double your chances of winning. Probability is not just about the remaining doors, but the information revealed by the host. Traditional code is deterministic. It takes an input and returns a single, fixed output. This works for arithmetic but fails to capture the nuance of real-world complexity. Probabilistic programming changes this. Instead of a single value, the code outputs a distribution of possible outcomes. This allows AI systems to mathematically represent uncertainty. By coding models that think in terms of probabilities, developers build systems that can reason through ambiguity, effectively calculating the likelihood of different scenarios rather than guessing a single fact. Standard probability models often struggle to explain human decision-making, especially when choices seem to violate basic logic. In classical probability, we assume a path must be taken. However, human choices sometimes reflect a state of superposition where multiple options influence the final outcome simultaneously. This results in a violation of the law of total probability, a phenomenon economists call irrational, but which quantum probability models can explain quite effectively. By applying a quantum probability framework, we model decisions using interference patterns rather than simple sums of outcomes, capturing the complexity of human cognition. Traditional health models rely on population averages. They treat every individual as a data point in a broad distribution, often missing the unique nuances of your own biology. Modern health technology changes this by collecting real-time sensor data, tracking heart rate, activity levels, and glucose to build a probability model specific to you. By shifting from general averages to personalized probability, we can precisely calculate your unique risk for health events, enabling proactive care instead of reactive treatment. Risk literacy is a vital life skill. We are constantly flooded with information about global events, medical advice, and financial choices. Without this skill, we fall for cognitive biases that cloud our judgment. Probabilistic thinking helps us replace snap judgments with measured uncertainty. To be risk literate, we ask for base rates and evidence quality instead of accepting headlines at face value. Ultimately, risk literacy is about empowerment. It allows us to navigate a complex, uncertain world with confidence and clarity. We have traveled far in our study of probability. We've learned that the world does not operate on certainty, but on likelihoods. The goal of probability isn't to be right every time. It's to be better calibrated. It's about ensuring that when you say something is 70% likely, it happens 70% of the time. Embracing uncertainty is not a sign of weakness. It is the most scientific way to navigate our unpredictable world. By thinking in probabilities, we transform fear of the unknown into manageable risk.